Dear students, on this clip, we're going to be going over an example on how to derive what the derivative of tan x is using the definition of derivatives with limits. So let's go ahead and write down the question, what we're going to do. Prove that, this is part 3 of a 3-part series. Part 3, I did the part 2 and 1 for sine and cosine. You can view them with the links below. For part 3, prove that the derivative of tan x, or prove that d dx of tan x equals secant square x. Okay, I want you to prove this. I'm going to prove this using the limit definition. Definition. I can't write anymore. The limit definition of the derivative. Okay. All right. Okay. Let's go ahead and start. But before I start, I want to write down some key formulas that we have to know before we start the proof. I'm going to be making use of all of them. I'm in the process, so let me state them first before we start. Okay. So key formulas. Write these down. First one is the definition of derivative using limits. So d dx, derivative of a function, basically is the limit as h approaches 0 of f of x plus h minus f of x over h. Okay, so there goes the limit definition of the derivative. Number two, 3, and 4 are going to be trigonometric identities. So the first one is a sum identity for sine. Remember, trig sine x plus y is basically sine x, uh, sine x plus sine y plus cosine x sine y. Sometimes I forget these things. All right, number 3, we need the sum identities for cosine x plus y. For cosine, remember, just keep the trig function and flip the signs. Okay, that's how I remember how to do it. So you just have cosine x, cosine y. Whenever the trig function stays the same, you have to invert the sign, minus sine x, sine y. Okay. All right, and then the fourth one, which is also trigonometric identity, is the Pythagorean identity. So sine square x plus cosine square x equals 1. Okay, remember the commutative property of addition. We can also express 1 as cosine square x plus sine square x. Remember, the order of addition doesn't really matter. So it could be in this formulation or that, they will equal 1. All right. Formula 5 that you are going to need is a limit law. We don't have too many limit laws here as opposed to examples 1 and 2. So the limit as h approaches 0 of sine h over h equals 0. This is the sandwich theorem. Oh, sorry. Equals 1. This is the sandwich theorem. I have a clip that I went over. You can make a search for it that shows you the result of this. So you can verify this with your calculator. Sandwich squeeze theorem for you. Okay, and then formula number 6 is identity. It's not a complicated identity. It's a reciprocal identity for two functions. So you just need to remember that secant x equals the reciprocal of cosine 1 over cosine x. Okay, so we have all the key formulas that we need to execute this proof. I'm going to be making reference to them as we go. Let's go ahead and get started. Okay. All right, so proof. What are we trying to prove? Let's state what our objective is first before we start. Let f of x equals tan x. So if x is equal to tan x, we must show that derivative of tan x equals, what's the derivative of tan x? Secant square x. Okay. If I can show that the derivative of tan x equals secant square x, then I'm done. All right. So let's start with the function. The function that we're starting with here, f of x is equal to tan x. Okay. Now, if f of x is tan x, what is f of x plus h? It just simply means our inputs changes from x to x plus h. So f of x plus h is going to be tan x plus h. All right. So we're proving, we want to find out what the derivative of the function is, ddx of the function, which is basically ddx of tan x. So first formula I'm going to use, scroll off to formula 1, the derivative of limits. The definition of derivative using limits. So let's apply that here. So we're going to have the limit as h approaches 0. The formula tells me f of x plus h. So f is tan here. So instead of f of x plus h, I'm going to write tan x plus h minus f of x, which is just tan x. And then that whole story divided by h. Okay. There's another identity that I'm going to use. I forgot to indicate it. Let me add it up here. I'm going to use it right now. Let's put it as formula number 7, which is the quotient identity for trig functions. Okay. I forgot to state that tan x equals sine x over cosine x. I know most people know this, but I still have to state it anyway. I can make any assumptions. All right, so tan is sine over cosine. I'm going to make use of this quotient identity right now. Okay, so this is going to become, I shift it to the right because it's a little bit long, the limit as h approaches 0. Instead of tan x plus h, I'm going to use my quotient identities, formula 7. I'm going to be sine x plus h divided by cosine x plus h, because tan of an angle is the same as sine of the angle divided by cosine of the angle, minus tan, minus sine x over cosine x. All right. Okay, now we have that fraction in the numerator is going to be divided by h. Okay, divided by h. Now, what I'm going to do is I'm going to find LCD in the numerator and then combine the numerator as best as I can, and then resolve the denominator with this denominator here. So what is the LCD here? This is cosine x plus h. The LCD is cosine x times cosine x plus h. So I need a cosine x plus h here, so I'll insert it top and bottom. Cosine x plus h, I'm going to multiply by the top and the bottom. That's the version of 1, cosine x plus h. And then on the right side, cosine x. Okay? So times cosine x on the top, and then times cosine x on the bottom. Okay? Part of my writing. Let me make it part of the way. Let me erase this. So what I'm trying to do is I'm trying to make the denomination the same. Okay? So I'm just going to push back my limits a little bit. Limit is h approaches 0. So we have a cosine here, I need a cosine here, top and bottom. So on the right side, I'm going to times it by cosine x and cosine x. All right. All I'm just looking for is the LCD. I want the denominators to be the same. So the target LCD is cosine x times cosine x plus h. All right. So what I'm going to do is I'm going to distribute. What I'm going to do is let me go ahead and express them as a common fraction with the same common denominator, and then I'm going to start making use of my identities. All right. So I'm going to include a lot of intermediate steps so we don't get lost in the symbolic manipulations. All right, so we're going to have limit as h approaches 0. Here on the top we have times cosine x times sine x plus h up here, minus over here sine x times cosine x plus h, And so they have the same common denominator, we'll just express them as a unified common denominator, which is cosine x times cosine x plus h. All right, that's for the numerator. Since we're divided by h, why don't I put it to the side here? Divided by h over 1. All right? Okay. Now we're going to make use of formulas 2 and 3, the sum of difference identity, to break down this sign, which is the sum of two angles, this cosine, and then this cosine. All right? Let's go ahead and break this down. We're going to have the limit as h approaches 0 of cosine x. Let's put the cosine on the outside and focus on finding some identities for sine, which is sine x. Let's see what we're about cosine h. We switch the identities, remember, to keep the sign plus cosine x sine h. All right, that's for this piece. On the right side, minus sine x. And then the cosine identity keeps two functions with the sign. We have cosine x, cosine h. Notice the two functions are the same, so switch to sine minus sine x, sine h. Okay. And look at the bottom. You notice that we can break down cosine x plus h also, right? So let's go ahead and do that. So with the cosine on the outside, cosine x, and then times, applying the sum identities for cosine again. Here we're going to have cosine x, cosine h, keep the trig function of the same. So put the sine minus sine x, sine h. This is basically what we did up here. All right. Okay. Now let's see. Where are we? What we're going to do next is basically distribute. Okay. We're going to distribute. Then it's going to look as messy as it possibly can, and then it starts looking nice after that. All right. So I'm going to distribute this cosine to this term and this term, and then distribute this sine to this term and that term. This cosine downstairs here. Oh, wait a minute. Yes, I'm going to distribute to this term and that term. All right, you notice you're missing something? Divided by h. So what does it mean to divide by a fraction? So to divide by h is the same thing as to multiply by its reciprocal, right? So times 1 over h. All right, I'm going to put the h somewhere here. Okay, I'm going to leave it alone outside. All right, I'm not going to distribute it. You see why in a minute. Okay, so now let's go ahead and distribute the trig functions to the sum of difference identity. The sum identities I just did. So in the numerator, I'm going to have, let's see, sine x, cosine x, cosine h for this one, and then for the second one, plus cosine squared x, cosine and cosine squared x, sine h, minus on the right side, I'm going to have sine x, cosine x, cosine h. Oh boy, I'm running out of room. Minus times minus is a plus. Sine square x. The sine times sine is sine square. Sine x times sine x is sine x. Sine square x. Sine h. That's for the numerator. And then that whole 3 divided by the same thing at the bottom. We're going to have cosine square x, cosine x times cosine x, cosine h, minus, and we can have cosine x, sine x, sine h. Okay? Pardon me for going over these, so I'm trying not to lose my face here. All right, so there you have it. And in this h over here, I'm going to put it outside. Okay, don't distribute it in. Okay, that's a waste of time. Leave it alone outside there. Okay, now this is as bad as it's going to get from us. Okay, it's going to start getting nicer now. So let's take a look at what we have. If you notice, we have opposites here. Two terms that are opposites. So this is the opposite of that. When combine opposites, what happens? They add up to 0. So this one and this one add up to 0. And then on the numerator, we're going to have limit h approaching 0 of cosine square x sine h plus sine square x sine h, all right, divided by same, the denominator stays the same, okay? So let the denominator as it is, times, let me see, can I do something different? Not yet. So times h times cosine square x, cosine square x, cosine square x, cosine h minus cosine x, sine x, sine h. I'm doing a lot of intermediate steps so I don't get anybody confused. I know some of you are really smart and you can skip a lot of these steps in your head. So that's fine, but I gotta write everything down so you understand what's going on. All right, so now let's take a look at the top. You notice that sine h is common to a term, so I'm going to factor it out, and then that will make it possible for me to, oops, sorry about that. That'll make it possible for me to use, the, one of the formulas, basically. It'll make it possible for me to use the Pythagorean Identity, formula number 4. Okay, so let's go ahead and do that. So we're going to have, on the top, limit as h approaches 0 of factor out sine h, and they're both common, so we have sine h. And then I'm going to be left, I'm going to color code it so you see what's going on with cosine square x plus sine square x, okay, in the parentheses, and that will be divided by h times this story here, cosine square x, cosine h minus cosine x, sine x, sine h. Okay? All right, so that divided by that. Now, what we're going to do is make a first substitution. So we have the Pythagorean identity here. So this one can be replaced with 1. So while we're at it, we can also separate this product right here. So now we're going to have the limit as h approaches 0. You see these two? I'm going to write it in blue, actually in green, of sine h over h times, now over here, this is 1 divided by, divide this whole thing by this whole story right here, which is cosine square x, cosine h minus cosine x, sine x, sine h. Okay? All right, now we're going to use the product property of limits to finish this off. So the limits of a product of two functions is the product of the limits of the independent functions. So what we're going to do is distribute the limits to both of these two functions right here. We're going to have the limit as h approaches 0 of sine h over h times the limit as h approaches 0 of 1 divided by this story right here. Let me move it up. Divided by this entire denominator, which is cosine square x, cosine x minus cosine x sine x sine h. Okay. All right. So on the left side, we're going to use this limit law we talked about, formula number 5. The standard term for sine theta over theta is 1. So we're going to apply that here. Okay. So it's going to become the limit of sine h over h is 1 times. Now, using the limit law, you can just substitute the limit into the values of x here. If you notice, one of my variables has just changed. This is cosine h, so this is supposed to be cosine h. That would have been a problem. So now I'm going to substitute 0 for all my h's in this denominator. All right. So we're going to use, because the limit also distributes to the denominator. So in this case, we're going to have 1 divided by, we're gonna have, let me apply the limit laws here so you guys do not get confused. We're gonna take the limit as h approaches 0 of cosine square x, this is going to be long. I'm going to need more space for this. Okay, I'm going to write narrow so that it fits. So we're going to take the limits of each and every term in the body. All right, so limit as h approaches 0 of cosine square x, that's the first dictate, and then the limit as h approaches 0 of cosine h. Next one, minus, distribute the limit to these three also, limit as h approaches 0 of cosine x, times the limit as h approaches 0 of sine x, times the limit as h approaches 0 of sine h. Okay? A little bit long. I thought it was not going to fit, but it does. All right, so let's evaluate them term by term. So this 1 is the multiplicative identity, so we just forget about that. So we have 1 divided by fix my line. Let's see. So this is independent of this limit, so it remains cosine square x. The limit is h approaches 0 of cosine h. You plug in the 0 into h times cosine 0. We're going to evaluate that minus. This is independent of the limit, so say that cosine x, because these variables are the same. This is independent of h. Whatever h does doesn't bother sine, so sine stays. And then this one, we plug in the h into 0 times sine 0. Okay? All right, getting there. So that's going to become 1 over cosine square x stays the way it is. Cosine 0 is 1 minus cosine x times sine x. Sine 0 is 0, right? So that's going to close the problem here. So we have cosine x sine x times 0. Okay? So what do you notice happens over here? So this is 0. You multiply all these terms by 0, they'll go to 0, right? So you're going to have, they're all equal to 0. So you're going to have equals cosine square x is just times 1 is just cosine square x minus 0, which equals 1 over cosine square x, which equals 1 over cosine x squared. All right, so now we're going to make use of the last identity. What is 1 over cosine x? Secant. Secant is 1 over cosine x. So that's what we're going to do here. We are going to use our reciprocal identity for trig functions to do our last substitution. So we're going to have secant x squared. The standard form for writing it is basically secant square x. Okay, so basically the derivative of our function, which was the derivative of tan x, is equal to secant square x. That completes our proof. Okay? So thanks so much for taking the time to watch this video. Please subscribe to my videos here to help support my site. You can share the contents of this video over Facebook and Twitter with your friends. More videos coming from my.com. Thanks again and have a wonderful day.